Hello again. We're going to talk about two different distributions in Module 2, the binomial and the normal. And we need to talk about the binomial a little bit in the terms of the formula. We're going to approach it from two different standpoints. We'll either be calculating by hand or we'll be using tables. So we're going to start with calculating by hand, and then we'll learn how to use the tables in a little bit. Before we actually use the formula, we need to do a little bit of review on factorials, just in case you don't remember. And if you remember your factorials, then you can just listen or shut this off. But anyhow, if you cast your mind back, n factorial, that's a really sick looking n. Let me erase it and clean it up. That's a little better. N followed by an exclamation point, that's n factorial. And that's n times n minus 1 minus times n minus 2 dot 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 times 2 times 1. That's the product. That's a squiggle. Let me erase that. So these are all multiplications. So if I have 4 factorial, that's 4 times 3 times 2 times 1, or 24. Okay? And most of you will have a button on your calculator that will do these. By definition, 1 factorial is 1. Similarly, 0 factorial is 1. It's something out of differential equations. Just accept it. Yes, I know how it works. No, I'm not going to tell you, it's a secret. Okay. So anyhow, let's change. Now we're going to do something called combinations, which again you may or may not remember, which is part of the formula. And that's just a set of factorials. You have n factorial taken x times n minus x. And that's pretty slick. Quick note, when you do that n minus x, the quantity factorial, do the subtraction first, then do the factorials the last thing. So for instance, if I have 7 minus 5 factorial, you want to do the subtraction first. So that's going to be 7 minus 5, which is 2 factorial. And 2 factorial, of course, is simply 2 times 1, or 2. It's not 7 factorial minus 5 factorial. Do not do that, please. Okay, so if I have something to the effect of, how about 8 factorial over 3 factorial times 8 minus 3 factorial, what am I going to get? So I have 8 factorial in the roof over 3 factorial times 5 factorial in the basement. Well, we can actually do some pretty cool stuff with this, in the sense that I can write that 8 factorial as 8 times 7 times 6 times 5 factorial, and then I have 3 times 2 times 1. That's my 3 factorial times 5 factorial in the basement. So the 5 factorials just cancel. 3 times 2 times 1 has another name, it's 6. I can cancel that with a 6 there. I'm left with 8 times 7, better known as 56. Okay? So those are really pretty easy when you think about them. It just takes a little bit of practice. And with any luck, you have a key on your calculator that'll do it for you. Look for something that says like N, either something like this, NCR, with the little C preceding the N. It might be N, oops, where's my, there, N, C, comma, R. Look for things like that. Or it might be C, N, comma, R. Look for that. If you've got the graphic calculator, go to probability and scoot down a couple on there. You might see it there. Okay? So that's the warm-up to the formula. Now let's look at the formula itself. This is for the binomial. Let me change page. So the actual formula looks a little sneaky and evil. It's not so bad once you've done it. Of course, it's easier if I can write. Huh. What's wrong with my stylus? Whoa. Here. The probability of x is equal to n factorial over x factorial times n minus x factorial times lowercase p to the x times 1 minus p to the n minus x. Don't panic on me. And x runs from 0 to n inclusively. P runs between 0 and 1. Actually, it runs between 0 and 1. In this particular case, P does not take on the endpoints. If it does take on 0 and 1, essentially the probability goes to 0. Okay? Now, these are always going to be context driven for us. There'll be some little story. The P is going to be given. It represents a probability. Whoops. I can't spell tonight. Can't spell most days. Probability of success, and I'm going to put success in quotes. Success is going to be context driven given the problem. And N is the number of trials. Okay? So the binomial, you're going to be running a set of trials, N trials, and the answers are all either yes or no's or zeros and ones. It's binary answers. There are no maybes. Either you do or you don't. Okay? The trials are independent, and what that means is what the answer is in the first trial has no impact on the second or the third or the 352nd, whatever the n happens to be. And that's good. Okay? So let's make up a story and let's put it together and see how it works. So let's say we have n equal to 5. Oh, how about light bulbs? Light bulbs. And we put them in our little workshop. And we know, because it says on the package of the light bulbs, that the probability that the light bulbs will be on is 0.9. Okay, 90%. And we want to find the probability find the probability that 4 lights are on when we walk into our workshop. Okay. So, n is 5. That's our total number of trial. Oops. Oh, those n's. They're getting real wild today. N is 5. X is 4. That's the number of light bulbs. Or I should say the light bulbs that are on. That's our number of successes. The probability of success is 0.9 or 0.90. So I want the probability that x is equal to 4. So we plug into our formula. So we're going to have 5 factorial over 4 factorial times 5 minus 4 factorial times, okay, it's p to the x, so it's going to be 0.9 to the 4th times 1 minus 0.9, that's 1 minus p, raised to the 5 minus 4 power. Okay? So let's start doing some number crunching. So I'm going to have 5 factorial over 4 factorial times 1 factorial times 0.9 to the 4th times 0.1 to the 1st. Okay, so things are going to start cleaning up here real nicely in a second. All right, let me do a little calculating. So I'm going to have 0.9 raised to the 4th. Okay, hang on. All right, we'll come back to that in a second. So that first term, I'm going to have 5 times 4 factorial over 4 factorial, and 1 factorial is just 1. 0.9 to the 4th is 0.6561. 0.1 to the 1st is just 0.1. So the 4 factorials cancel. I have 5 times 0.6561 times 0.1. And I'm going to multiply all those together. Let's see. Times 5 times 0.1. And what are we going to get? 0.328. Okay? So the probability that 4 of those light bulbs are on is 0.328. Pretty cool, huh? All right. And always remember, if you have 2 friends named Naomi, you are binomial. Thanks.